Thank you very much, Simon. Thank you very much for organizing such a great conference. And so I set up this experiment at the Fritz Haber Institute of the Max Planck Society in Berlin, and recently moved to Imperial College in London, where we now set up the second generation of these experiments. And just briefly, I want to mention the quick history of laser cooling atoms and molecules, so you can appreciate a bit the progress that we've made so far. And with the atomic case, you see that the first mod was 87 and then BC 8 years later. So, and I also want to highlight here that from very early on, people were already thinking about these alkaline earth atoms because of the unique properties, especially in the early days because of the collisional properties to reach a BC. But then it took a bit longer to actually reach a BC of these alkaline earth systems. And I want to highlight here also that it's with this alkaline earth system, it's actually possible to laser cool directly to degeneracy. So this will be important for molecules at some point, I think. So if we compare this to the molecular history, or laser cooling history, we start with very few, 800 molecules at a base density of 10⁻18. But now, 10 years later, we've already bridged 10 orders of magnitude. So I think this really nicely highlights the rapid progress in the field. And hopefully, we'll see a BEC very soon. And so if you see the first one was 2014, and in the atomic case, it was 8 years, so we are slightly behind, but I think it's not very far away. Why alkaline earth atoms in the first place? So there are many reasons, right? But it always comes back to this structure here where you have a singlet ground state and a singlet peak side state with a very strong transition. Here I draw my favorite alkaline earth-like atom, which is cadmium. And you have this triplet metastable state that offers this new toolbox to laser cool to very low temperatures, to use it as clocks, and now for quantum information, even searches for new physics. So why do we want an alkaline earth-like molecule? So obviously new species, new fun, right? So for me in particular, the interest was to boost the molecule number in the mod. As you know, we're still struggling a bit with the number that we deliver into the mod. So I really wanted to push this to be comparable to the atomic case. So reaching about 10 million molecules in a mod with densities reaching 10 to the 11 per cubic centimeter. And I wanted to actually also use metastable states and use these metastable states for a new resource for laser cooling, but also for new physics and to try out new things. What limits the number of molecules in a mod? At the moment, all molecular mods use this kind of what I call rubidium-like molecules. So it's an alkaline earth with a fluorine attached. All these sources are very inefficient, so you produce very few molecules compared to atoms. So an atomic beam, they're all radicals, so they react very quickly in the source. The sources are pulsed, and because you have this complicated structure of molecules, the optical cycling is actually relatively slow. This leads to long slowing distances, and because we have no easy way, or like Silke showed, there is maybe a way to implement a Zeeman slower. There is no way to accumulate now. So we load a single pulse of very few molecules into a magneto-optical trap. Obviously, that limits the density. And even worse, the capture velocities of these mods is extremely low. So we need to slow to very low velocities, again, exacerbating these losses. And hopefully by the end, you'll see that these alkaline earth-like molecules that are proposed to provide a solution to all these. So what do I mean by alkaline earth-like molecules? So maybe we can already go straight there. So it's a singlet sigma ground state and a singlet pi excited state. They're usually composed of this boron group, so BH, Br, or aluminum with a hydrogen or halogen attached. It's a bit surprising that you think that you can laser cool these because now you have like 2 unpaired electrons here. And we always think of it that in case of calcium fluoride, you know, they pair up and you have this single dangling electron that's centered on the calcium atom. And you just cycle and talk to this electron, and then you can cycle many photons. With aluminum, this case is a bit different because you have these 2 electrons now. But it turns out that one of them is actually also just centered on the aluminum atom, and you can do it exactly the same way. It turns out that the Frank-Collin factors are actually much better than for these molecules than they are for these alkaline-like. Just to compare this quickly to the respective atoms, so you see that calcium fluoride compares reasonably well to rubidium here, with the slowing distance that we typically achieve in the labs is not quite as close to the ideal case. So the scattering rate is not always exactly like the maximum that we would like to get. And when you compare this to AlF or cadmium, it's considerably short. So it means this optical force that we can exert on these molecules is orders of magnitude higher. Leads to a shorter slowing distance, larger capture velocity, and we can mitigate most of these issues that we have so far. I chose to work with the AlF molecule because it has a very strong molecular bond, so there are no reactions at high density, so you can really produce them very well in a source. It has this strong transition here in the deep ultraviolet, which leads to this very short slowing distance and large capture velocity. It has this metastable triplet states that I would like to work with, especially with this narrow line cooling in mind, that I can cool the molecules to or close to the genesis to very low temperatures without evaporation or collisions. And as we know, collisions are quite messy for these molecules, so if I can avoid them in the first place, would be great. A big worry or a big concern was in the beginning this leakage from this singlet pi state down to this triplet manifold. So a quick calculation thought, okay, it's not an issue, but then when we actually measured this leakage rate, it turned out to be an order of magnitude larger because there was an unknown B triplet sigma state here that would actually, the spin orbit interaction was a bit larger than this A triplet pi state with this singlet pi state. As you can see, we have all this, we've got really narrow lines and not so narrow lines that we hopefully can use for laser cooling. But as you can see, 85 Hertz line width is not an amazing narrow line to do actually laser cooling or narrow line cooling. So we have to now rely on repumping or like shortening the lifetime of this triplet state by coupling it to the singlet pi state as well. Just want to remind you that the spontaneous scattering forces that really rely on scales really with 1 over lambda to the power of 4. So that really shows you how powerful this can be. So new species, new challenges, new surprises. Maybe if you've seen Tim's talk, you always start from a very empty slate and you need to do a lot of spectroscopy. So we spent about 2.5, 3 years just exploring all the different possibilities of different states and actually do very high resolution spectroscopy on it. Then measure the dipole moments, define a hyperfine structure, all the lifetimes of all these states, find new ionization schemes to actually detect these triplet molecules, close the cycle from going from the singlet ground state to the triplet state back to the singlet state to measure the transition dipole moments so that we can really like very confidently come up with a nice narrow line cooling scheme as well. And especially an accumulation scheme. So what you see here is just a pulse laser excitation to the triplet pi state, very crude pulse dye laser spectroscopy, the PQ and R branch. Then we can replace this pulse laser with a CW laser and we can immediately resolve this hyperfine structure in the excited state. And then we can even drive microwave transitions within this triplet manifold to then measure this hyperfine structure with kilohertz accuracy. And that's actually quite nice because it's a really good benchmark molecule now for quantum chemistry calculations as well. What's the catch? These deep UV lasers, they're very complex, they're prone to degradation. We have 4 in Berlin now with typically 2 to 3 are operational at any given time. So, but you can see it's progressing well. So we started with 50 milliwatts and already within 4 years could increase it to 720 milliwatts. So what's the solution? We came up with actually replace all these complicated lasers now with a new system that's based on VCSELs and new doubling cavities. And we teamed up with nice new companies that are hopefully a bit more reliable. And so how do we do this? We replace first of all this TISAF laser with a VCSEL, so a vertical cavity surface emitting laser. Then we integrate this first doubling stage into the VCSEL so that we get rid of one doubling stage. And then we replace actually this UV doubling stage with a new design that uses elliptical focusing to actually reduce this photo-induced damage. What's the status now? These before these in Berlin, they're still our benchmark system. Then we've got 2 of these now running in London that actually work quite well. We could reach already in this first stage doubling efficiency of over 70%. We haven't reached 700 milliwatts yet because this is also already a new design that's not been optimized to the maximum yet. But I think we're making good progress here. And we also have our first system now of these intercavity VCSELs where we just have a single laser or a single box, or it's not just composed of two little boxes that can actually be serviced very nicely. And it's already considerably cheaper than it used to be. So we have a few setups now built over the years. So there's a supersonic beam machine, there's 2 cryo beams in Berlin. There is a new cryo beam now, the 2nd generation apparatus in London already with this laser development. My postdoc Sid Wright now took over the labs in Berlin, and it's still a very nice, friendly collaboration. What does the buffer gas beam now look like? I told you that because it's such a stable molecule, we can produce it in very large quantities. And if you look at this, it's a typical time of flight. So single laser beam, just testing, the molecules fly through the laser, they fluoresce, and you see a big peak. And if we make the molecules in the same machine with, we could just, have multiple ablation targets and produce magnesium fluoride, calcium fluoride, YBF, and you'll see we get over an order of magnitude more molecules, just because they're more stable and they don't react in the source. We can also compare it directly to the atomic beam that we generate via ablation. That's the beauty of having these tunable lasers. You can just, within a couple minutes, go to a different species and then see what's going on in your beam. What happens here is, for example, in the aluminum case, we measure the aluminum beam here with no fluorine present in our source. And then we add this fluorine, and then you see a big chunk of it is lost. And if you then look and actually measure the AlF beam, it actually fills up this gap very nicely. So that means that the reaction efficiency is extremely high. And we nearly convert 100% of our aluminum that we produce into AlF molecules. So electronic branching, obviously this is an issue, and we had to measure this very carefully. And so you need to do spectroscopy on the 10⁻⁷ level. And this is quite a challenge, or was it? Took a bit of time to calibrate your detector, find a detector that can actually cope with a dynamic range of 7 orders of magnitude. But in the end, we had 2 techniques where we just excite the molecules here in the strong transition and then measure the decay into the triplet state. We're using specific filters that we found. And then the other way is just to excite the molecules to the triplet state. And then from the triplet state with the CW dye laser back to the single state, measuring the transition dipole moment, and then measuring the decay back to the ground state in the UV. What you see here, the black curve is the UV, like where we get a photon counter, typically about 10 gigahertz. And then when we measure this decay down here, you can see it's on the order of kilohertz. So the branching is large, but not too large. We actually don't want it, to be too small either, because then the narrow line cooling scheme won't work. So it's actually right where maybe a bit too small. So, but it's fixable, because with about a watt of CW laser at 597, we can actually couple it quite nicely to this single pi state, shortening the lifetime of this triplet pi 0 state. So we had to measure the triplet pi lifetime as well, because that wasn't known. So this was a very lengthy measurement, but in the end we could measure it, and it turns out to be on the order of 2 milliseconds. And the nice thing about molecules is there's not one lifetime, there's many lifetimes depending on the J state that you use. So what you see in this plot is just the distribution of different lifetimes you can have for the different rotational states in this triplet pi state. So you pick your favorite lifetime for the application you have in mind. It's a really cool new resource for laser cooling molecules as well, because scattering photons is a very pressured resource. This means that I can load a MOT, basically transfer these molecules into the triplet state, and they would just be trapped in the magneto-optical trap, so in the B field gradient. They will then just decay back down and rejoin the optical cycle. So it's a very nice way, first of all, to accumulate, but also to reset my photon clock. So I don't actually need to close all these repumps. I only need one repump laser, scatter 10,000 photons, park my molecules in the triplet state, they will come back and they will rejoin the cycle. So obviously it has a narrow line and provides high resolution. And because in the triplet state you also have a magnetic moment, you can now turn on your magnetic moment or turn it off, just by adding a single laser. So vibrational branching, obviously, that's always the first thing you also need to check is that's very nice because we have the strong transitions. You can actually just couple the fluorescence of your molecule into basically a large optical fiber, put it into one of these small grating spectrometers, and then you immediately see that the vibrational branching is indeed very small. It's the advantage of using these very strong transitions because your signal to noise is just incredible. So all Q lines of these transitions are closed, so we can actually laser cool many rotational states if we wish to. So we're not like bound to a single one. So on this Q1 line, we can scatter over 200 photons, and then we can use the R0, the R1, or the P lines kind of as a standard candle, because they cannot cycle more than 3 photons, for example, on the R0, you just pump them to J equals 2. So by comparing the signal of the Q1 line to the R0 line, we know exactly how many photons these molecules scatter. There is, obviously, it's not such an easy molecule because you have the aluminum nuclear spin of 5 halves and the fluorine nuclear spin of 1 half. So this Q line has actually 72 levels. So our optical cycle is composed of 72 levels. And the excited state hyperfine structure is spans about a couple hundred megahertz. But because our line width is so wide, we can actually address all of these levels in the excited state as well. This is what you see here in the typical Q-band spectrum. So here you can see this unresolved, partially resolved hyperfine structure. And then for higher rotational states, the hyperfine structure collapses. And if you go to the triplet manifolds, then obviously you can see that you can resolve this really nicely because now you have this really long lifetime. Here's this first cycling experiments that we did by just comparing the R line to this Q line. And you see this massive enhancement in signal because the molecules now start cycling. And to our surprise, this even worked without polarization modulation. So you don't even need to modulate your polarization, which you usually have to do on these J1 to J1 transitions. It's just because the aluminum nucleus actually, the hyperfine structure provides us with a remixing of these dark states in the ground states. Just is an accident of nature, I would say. If we then actually turn on the polarization modulation, we can actually still scatter even faster with up to 50 photons per microsecond. So this means that within 100 microseconds, we can actually slow a molecular beam to rest. One surprise that always pops up with the new molecule that we didn't really anticipate is that when these molecules are in an electric field, the optical cycling stops. So what happens is that the lambda doubling in the excited state is actually small, so the different parities mix in small electric fields. And if you turn this electric field up, this population that we measure in this V equals 1 in the ground state pops down, so they stop cycling. So that means we need actually good stray electric field control, but it also means that when we polarize the molecule, we need to rethink the optical cycling scheme to repump some of the extra leads. But we can also use this to actually increase the signal in our laser cooling state, because what we can do is we can just apply an electric field, pump the molecules, for example, on this R0 line, because there's no defined parity anymore. We can enhance it by a factor 3 and pump all these ground state molecules into our laser coolable state J equals 1. We can then pump them into V equals 1 and then back from V equals 1. So this is the first step that you can actually close this optical cycle to a level where you can now load them up. And to measure really the acceleration or the spontaneous scattering force, the best way to do this is usually by optical deflection. And we could really see that with a single laser beam of about 4 millimeter diameter, we can actually push with no polarization modulation, no sidebands, no complicated structure. The laser goes straight from the laser output into the chamber with a couple mirrors. And you can deflect it, and you can actually infer an acceleration of about 1,000 kilometers per second squared. So this is exactly what I showed you in the beginning. It's about 100 times higher compared to strontium fluoride, for example. This results in this big capture velocity that's at least 50 meters per second, but probably even higher. Then you can retroreflect this single laser beam. So now you have a standing wave. You put a lambda by 4 plate, and then you can actually check if your subdoppler cooling works as well. So we not only rely on narrow line cooling, but we can also do subdoppler cooling. We use this just to collimate our molecular. So we need about 4 lasers to really slow and capture these molecules in the MOT. And as I said, that's a bit tricky. So what we did first is to use actually cadmium as a dummy atom. So where we only need 2 lasers, one slowing laser, one for the MOT. We produce the cadmium atomic beam exactly in the same way as before, where we just ablate the cadmium target. We cool it with cryogenic helium buffer gas, and then first do spectroscopy. And it turns out the isotope shift spectroscopy of cadmium was the quality and agreement of the results is somewhat disappointing. So people use this to actually extract nuclear charge radii, and so we spent quite some time to actually improve and actually solve some issues that we found in the literature. We did this also on the narrow line for cadmium, so then we could actually measure this a lot more precisely, and then it turns out that this is also an excellent candidate to actually search for new physics via nonlinearities in a king plot. What does that mean? There's an isotope-dependent energy shift due to new bosons that are maybe due to undetected bit forces, for example. And for this, you actually need to measure these isotope shifts on the 1 kilohertz level. But before you need to do this, you need to know your standard model background very well. And for this, you need to know your nuclear charge radii very well. And for this, we actually teamed up with Ben, Kurt, and Vijaya to measure all these transitions in cadmium compared to new atomic structure calculations and understand really how the nuclear part actually affects these isotope shifts before we actually go further and then measure these isotope shifts with kilohertz spectroscopy. We can do this now also for copper, nickel, silver, and zinc, all in the DPOV. It all turns out it is very useful for this, especially for radioactive nuclei at accelerated facility. We then went on and actually just to show that we can really slow these species in this deep ultraviolet in a very powerful way. We have just a single permanent ring magnet here that's 8 millimeters, about 50 milliwatts of counter-propagating laser beam. And then you can actually slow for here a cadmium atomic beam from about 150 meters per second to 0 within 8 millimeters. This, for AlF, we haven't managed to implement the Zeeman slower yet, but it's operating very similar to the cadmium. The arrangement is slightly different, but the size is very similar. So it's about 2 centimeters long, and it's composed of basically 2 fridge magnets. So very simple way to implement and boost our capture velocity from about 50 meters per second to beyond 250 meters per second. So now we built the MOT apparatus for cooling AlF, but first we loaded cadmium into this MOT, as I said, until we really get a handle on all these lasers. And what you see here is that we now really can reach a record density of more than 10 to the 11 per cubic centimeter with cadmium. And we can even already try out this first accumulation scheme. So this is very promising. So here you can actually see that we can boost the number of atoms we capture by about a factor of 6 to just by trying these accumulation schemes that we now want to implement in the molecule as well. Now we're approaching really like 10 to the 8 atoms here trapped at densities that approach 10 to the 12 per cubic centimeter. This was still done with permanent magnets because we need 500 gauss per centimeter or even more, because the strong transitions actually are very broad. So to shift them, actually, you need to go to very high magnetic fields. And the first prototype was a very crude approach where we just put in vacuum coils that can produce 700 gauss per centimeter, which works. It's a bit of a pain to use 100 amps in vacuum, but it's okay. We can make a cadmium MOT now, but it might not be the best strategy for the future. We simulated the MOT forces now for AlF, and they look very promising, where we can really reach this 1,000 kilometers per second peak acceleration rate, and they act over 100 meters per second. So this is very promising, but since we have a Zeeman slower, why not have a CW source as well? So then we can accumulate over seconds, not only a single pulse or maybe 10 pulses. And it turns out that you can produce AlF molecules actually up to a millibar very easily, and they actually thermalize with the chamber walls and survive multiple collisions. So now this opened up the idea that we could actually use a dispenser and load actually a molecular mod in a very traditional way, like a rubidium, like a typical rubidium. This was really driven by Sid, who then now also wants to try to actually couple here our cryocompatible organ with the buffer gas cell to bring this speed down and actually compress the rotational state distribution. And with this, I just want to conclude. So I hope I could convince you that AlF is now really a well-established and characterized diatomic, that we can produce it in very large quantities. We reach record high scattering rates and accelerations. And I hope that you can appreciate this triplet state is not really a nuisance as people thought of it for the atoms in the early 19th, but it's actually a really amazing new tool that we can hopefully use to really enhance the number of molecules, also the density we can reach in this modes. I showed you the cadmium is actually an ideal dummy atom for doing this, but also it offers so much more. And now we're actually spending quite some time also to cool it further and do this new isotope shift spectroscopy. And there seems to be really a way to load a molecular mod from a CW source. This I just want to thank the teams, and I want to just highlight the great work by the two PhD students, Max and Zeeman, who now both graduated, and with Eduardo, who is here and still has a poster if you're interested, and Sid, who now took over the labs in Berlin, and my new team at Imperial. Thank you very much.
Thank you very much, Stefan. Time for questions.
I have a question regarding the lifetime of triplet state. The first question is, because on the slide you have also the helium, argon. Could you explain? Because I do not understand fully, but it seems to be interesting.
So what do you mean? So the triplet state, right? So that basically means that it gets its intensity by spin-orbit coupling with the singlet states. So so that it's just an admixture. So if there would be no spin-orbit coupling between the two states, the state would live forever. But now, because there is some spin-orbit interaction, it now lowers it to about 2 milliseconds. It actually turns out that it was this B triplet sigma state that we didn't know about until we did the spectroscopy that actually causes the largest amount of spin-orbit mixing. Okay, and then because the spin-orbit mixing depends now on J, you can actually get, and on omega, you can now actually get many different lifetimes within one electronic state. It's very special.
Okay, I will try to continue this during the
Other questions? I have a simple one. How do I put this into time?
I think he's quite busy these days. Actually, he's already I think, towards most of Europe now. But yeah, you need to just book a slot.
Okay, I don't see any questions, and we're perfectly on time, so let's thank Stefan once more.